Oh no, surely not. But how long could derivatives possibly take? Okay, so we started a video on Friday, which was kind of building up to the idea of what we are going to kind of formalize today, which is the notion of a derivative. And what we saw was this idea that if I want to approximate or best estimate the behavior of my function, how my function is evolving, how my function is changing for a particular point, then the way to do so is to take the slope between the point at which I am concerned and a point that is very, 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 very close to the point that I actually care about. So for instance, if I wanted to know what was going on at, let's say, like 4, and I have some kind of function here, I'll say f of x is equal to, I don't know, the ln of x, right? And I want to know what is going on when x is equal to 4. That a really, really nice way to do this would be to let x be equal to 4. And then what would a good value for, sorry, x1, our starting value to be 4, what would a good value for x2 be if I'm really trying to pin down what's going on at 4? Yeah, 4.01. And then we could do the slope of this particular function using that point. In this case, slope we know is what, y2 minus y1 over x2 minus x1. How would I find the corresponding values for y1 and y2? Yeah, plug in the particular values for x. So if x is 4, what is y1 going to be if x1 is 4? Um, did you do that in your calculator? I was just saying like it would be just the ln of 4, right? You just plug 4 into the formula. And then if x2 is 4.01, then we could think of y2 as just whatever the ln of 4.01 is. And then we're doing slope formula with this, right? We're doing y2 minus y1. So this would be like the ln of 4.01 minus y1 ln of 4 divided by 4.01 minus 4. And that would give us a fairly good idea of what the slope is going to be like when we are in this vicinity of 4. How did we refine this idea? What did we do to make this an even better estimate, Andrew? Yeah, we just made our this little nudge to the right smaller and smaller and smaller by adding more zeros, right? Rather than looking at 4.01, we could look at like 4.00001. Here, look at 4.00001. And the idea is the closer this gets to 0, the closer this kind of nudge is to really not moving at all, the better a guess is that we are going to have for what is actually going on at the critical x value. Okay? And so the limit definition for a derivative is essentially just taking that idea and putting it into like this codification, and a very, very good way. And you'll notice I really don't use the limit definition. I really just use this slope intuition over and over again. If you find it helpful, is to just write out what your x1 and x2 are, and then what your y2 and y1 are going to be, and go from there. In this particular case, we're going to have our x1 just be x. And then we're going to have our x2 be x and then some, x plus h. And the idea here is we want h to be very, 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 very small, right? As close to 0 as we could possibly get it. The closer to 0, the better. How do we calculate our y1 and our y2? Well, all we are doing is taking whatever our function is and replacing the x in them with the particular x1. So this would be f of x1, which is just f of x. And this would be f of x2, which is just f of x plus h. And so our derivative, which we denote as f prime of x, is going to be the limit as h approaches 0 of our slope, y2 minus y1, which we say is f of x plus h minus f of x over x2 minus x1, which you can, if you want to, think of this as x plus h minus x, but how is this always going to simplify? Yeah, it's just going to leave behind an h, right? Because the x's are going to cancel. So that was the idea that we saw on Friday, the idea that we have this thing, the slope, and we can get a better and better and better estimate for what that slope actually is at a particular point by getting closer and closer and closer to the point that we actually care about. And then the way that we describe this, just kind of recall what this finds is the slope of the tangent line at that particular value of x. Okay, so we're going to look at two complicated examples, which I would not ask you to do on a test, just to kind of get a feel for how it works. And then we're going to look at two examples where you've done actually the simplification before, and you would be able to work it out on its own. What's the main issue with this particular limit just kind of as it stands? Why does this limit kind of inherently present some problems for us? Just by its construction. Yeah, Drew, what do you think? Yeah, we're dividing by 0 basically from the get-go, right? There's the construction of the derivative, the way it is set up. We can't do direct substitution right away, and we will never be able to do direct substitution right away because it will instantly be causing us to divide by 0. And so generally speaking, although the two examples that we're going to look at actually aren't going to have us doing this, but when we are able to compute these derivatives by hand, what that entails is we're going to try and get that h to cancel by simplifying the numerator as much as we can. Okay, before we take a look at some examples here, questions with our setup. Hopefully this is a pretty natural definition for what we saw from Friday, the idea of taking that slope and just getting it as close to the x value that we care about as possible. Okay, let's take a look at an example then. I'm going to start where I'm going to have you guys do A. A is fairly doable on your own, and then I have another example that I want you to take a stab at as well. Let's try B and C then. Those are a little bit tricky. They require a little bit of finagling. So we are looking at g of x is equal to e to the power of x, and we want to find the derivative denoted as g prime of x. This is like a little apostrophe. I had someone in second ask, is that a 1? No, it's a little apostrophe. Okay. So when I ask you for a derivative, what is that a fancy way of asking you for? It's a slope that has some kind of limit in it. Okay. And we know slope to be y2 minus y1 over x2 minus x1. What are always going to be our values for x1 and x2? Just always, 100% of the time, this is coming straight from the definition of derivative. X will be our starting value. It's the value of X that we care about is X. Okay, sure. And then what will X2 look like? X plus H. X, and then a little nudge to the right. Think of that as like 0.00000000001, right? Something very, 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 very small. If these are our X values, what are Y1 and Y2 going to look like here? What do I do to find Y1 and Y2? Yeah, so for Y1, we are replacing all of the X's with X's. Okay, that's not very interesting. That's just e to the X. And for Y2, what are we replacing all the X's with? X plus H's. This is e to the X plus H. How do we feel with the pieces for the slope? You have a question about where they're coming from? Okay, for sure. Okay. And we said that the derivative is a combination of the slope, but also a limit, right? So this is the limit as h is approaching 0 of y2 minus y1, in this case, e to the x plus h, minus e to the x, all divided by x2 minus x1, which you totally can write as x plus h minus x, but what's always going to happen with those x's? They're going to cancel. How do we feel about getting to here? Yeah, Hamza. There's nothing in the denominator to make the h cancel. The e to the x plus h minus e to the x, why doesn't that cancel? We are about to do some stuff with it, but they're not like terms technically. The x's are canceling because it's in the denominator. It's x minus x. Yeah, it's not interacting with the numerator. We would like it to be able to interact with the numerator, and that will come later. But for now, we're just simplifying numerator, simplifying denominator. Yeah. Other questions here? Reasonable? Alarmingly reasonable, hopefully. It's like, how could this possibly be calculus? Okay. From here, if I were giving you, say, I don't know if we had like a test on Wednesday, an example like this to do, which we will look at here in a moment, it would be a matter of simplifying the numerator to get the h to cancel. In this case, that's a little bit tricky. We're going to need to be a little bit clever with how we work our numerator. So let's think about what we have in the numerator here. H is going to be hard to simplify, so let's try and focus on what we can do with the numerator here. And I'm going to hone in on this e to the x plus h term. Okay, e to the x plus h. When I have, let's say like, I don't know, b to the 2 plus 3, where did this come from? How do we get addition in our exponents? What's maybe another way that I could write b to the 2 plus 3? B to the third? Absolutely. So we can split apart the addition in the exponent here. In this case, e to the x plus h. How could I split that apart? What's that going to look like? So e to the x times e to the h minus e to the x all divided by h. Okay. That's a solid start. Again, trying to simplify the numerator here. Looking at the numerator, what do we notice? Are they like terms just yet? No. So ideally, we would like them to combine in some way. Unfortunately, they're not like terms. If we don't have like terms, think of this as having like an x times a y minus an x. We would love to do out that subtraction, but they're not like terms. So what do we have to do instead? If I can't cancel, well, I'm not going to be able to get that to combine super nicely. So notice in this case, we have two things, both being multiplied by an x. We could factor the shared term out to the front. In this case, this is the limit as h approaches 0 of e to the x times e to the h minus 1 all over h. Limit as h approaches 0. Does that feel reasonable? Again, this one is not an example. This one's a little tricky. Normally, you would just simplify the numerator and the h would cancel. Okay. Now I'm going to apply some limit rules. We saw before, thinking back to the second lesson, that the limit works really nicely algebraically, right? We expect the limit to do the things that we expect it to do. For instance, if I'm multiplying two functions together, then when I take the limit of that product, I can get the same thing by taking a product of the limits. So I can kind of, and it's not this, but I can kind of distribute the limit through to a lot of different things. So another way for me to write this limit statement would be to say that this is the limit as h approaches 0. I'm going to separate out the stuff that has h in it and the stuff that doesn't have h in it. I'm going to take the limit as h approaches 0 of e to the x times the limit as h approaches 0 of e to the h minus 1 over h. A little bit weird. Yeah, here's. We're about to see because it lets us deal with part of this that is essentially not going to care about the limit, right? If I'm looking at this expression here, does the e to the x that I'm multiplying by care about what's happening as h goes to 0? No, it's kind of unaffected by it. So I'm essentially pulling it out to the side and I'm going to say, we're going to look at this one later because it doesn't care what happens when h goes to 0. We're going to focus on the stuff that does care what's going on when h goes to 0. And then we're going to have some stuff that like doesn't care about what's going on when h goes to 0. That was a why question, not a how question, right? That was like what is the motivation for doing it? Yeah. So essentially we're setting it aside for now. We'll deal with it here in just a second. And part of dealing with it in just a second is the fact that this is actually a very easy limit to evaluate. Do I have any domain issues with this first limit as h is approaching 0? No. What happens when I take all of my h's and replace them with zeros? What do I get? I just get e to the x, right? So this is a really nice limit to evaluate, actually, because there's nothing to evaluating it. This is just e to the x times this limit as h is approaching 0 of e to the h minus 1 over h. But this limit is a little bit problematic. Can I do direct substitution with this? No, still not. I'm still dividing by h. And if I can't do direct substitution with this, what was our other method for handling something like this? We're still going to have an h in the denominator, right? Because we would have, you multiply by 1 over h, and then you're still going to have that dividing by 0 issue. So algebraically, it's going to be tricky. So Harrison, what would you do? Yeah, plug in some numbers that are really, really close to 0 and see, do we approach something? And in fact, we've already done that. Flip back to the first page of notes. Scroll here. And what we find is that from example 2, subpart C is exactly this question that we asked before. It's just we're using h's instead of x's. So we've already done this one. And actually, we already did this one so that I could then back reference it so we wouldn't have to calculate it again. So actually, we already know what this limit is. This e to the h minus 1 over h is, in fact, just equal to 1. And so my limit as h approaches 0 is e to the x times 1, and thus my derivative of g is the function e to the power of x. Okay, a little bit of a weird one. Actually, this is like why e is my favorite number, is because it makes calculus so easy, where the function and its derivative match. Interesting. But where this kind of becomes, again, like, what is it even that we have found here, that we have this function that is the same? If I wanted to know the slope of the tangent line at a particular point, it is going to match the y value of that point. That is essentially what we are saying here. So essentially, if I wanted to know what is the slope of g when x is equal to 1, this is going to be e to the power of 1, which is just that value of e. Right? So this, again, slope of tangent line. We'll do some visuals here in just a second when we actually like compute some tangent lines. Okay. So again, the thing that I would be reasonably asking you on a test would essentially be to get to here. And then from here, it will be simplification rather than this weird like factoring process and knowing a limit and blah, 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 blah. But conceptually, do we have any questions about what we've done here for part B? How's this felt? Yes. Sure.
But we always at the limit.
Yes, so it is, okay, so there are a couple of different limit definitions. If you're using this one, which is taking the limit as you are looking at like x and then x plus h, this one will always go to 0. There's an alternative which looks at a particular point. If you want to find the derivative at a particular point, you can use the, let's say, we call... Let's call x1, we'll call this x still, and we could call x2 a, which is just some other number. So far, a here has just been x2, like x and then some, right? That's like the same thing. And here, you'll note that it's not that we're going to be having h approach 0. Here, we would say that it's the limit as x approaches a of f of x minus f of a divided by x minus a. So like there are some like weird ways to say the exact same thing, basically. but it's just the same thing, right? The idea is we want point number one and point number two to get super, super, super close to each other. If we are using the definition of the difference between the points, then the difference goes to zero. If we're saying this is the x value of one, this is the x value of the other, then technically this is approaching not zero necessarily, but whatever this x value is. It just depends on what definition you want to use. Yeah, good question there. But for our purposes, yes, if you're going to use this definition of x and then x and a little nudge, h goes to zero. That nudge goes to zero. Good question. And these are like, they're the same definition. So they look different, but they're identical. There's no difference between the two. To my knowledge, there is not. I could be wrong. That's why I unlist my videos, is so I don't have people telling me how bad I am at math. Good question. Other questions here? Okay. Let's take a look then at another example. Let's look at example C here, where we are told that h of x is equal to sine of x. Again, one that I would not consider to be particularly reasonable. I do not view this as one that is very feasible for us to use. Okay, so again, when I'm asking about derivative, what is that essentially a fancy way of asking for? Derivative is a fancy word for slope. And so what are our x1 and our x2 and our y1 and our y2? So x and x plus h are always x1 and x2. Very nice. Sine of x for y1 and sine of x plus h for y2. And so h prime of x is going to look like y2 minus y1, sine of x plus h minus sine of x over x2 minus x1, which we know is just going to leave behind an h. Right? X's are always going to cancel. And we want the limit as that goes to zero, right? Don't forget that. That's not our derivative. Derivative is when this h value goes to zero. So again, if you can do that setup from here, the simplification should be fairly nice. We should be trying to get the h to cancel, unless I'm giving you a very contrived one like this, which is going to require a little bit of planning and knowledge and blah, blah, blah. Again, not a reasonable one for what I would put on like a test, but it was still one that gets used a lot and one that's worth looking at. Okay, am I going to be able to do much to simplify the denominator here? Never. It's very simple. So then let's look at what we have for the numerator, where we've got this sine of x plus h term. Where have we seen this before, where we're taking sine of a sum? Yeah, sine of like an a plus b sort of deal. It doesn't distribute. Yeah, it was the unit 5 stuff. Sine is nice or mean. Sine is nice, which means gets along well with cosine. And is it going to do anything weird to that plus? No, it is not. Sine of x plus h is the same. Oh, that's not what I wanted. as sine of x times cosine of h plus cosine of x times sine of h. And so I can rewrite this. This is the limit as h approaches 0 of sine of x cosine of h plus cosine of x sine of h minus sine of x, all divided by h. And I think it'd be really hard to simplify the numerator without doing this. Yeah. Okay. What can we notice kind of similar-ish to what we were doing with the e to the x? What can we notice here that's kind of showing up a couple of times? So we got, yeah, some h's, sure, but like a specific term that's showing up multiple times. Because I only have one cosine of h. I only have one sine of h. Sine of x is showing up a couple of times here. Okay, that's interesting. So we've got this sine of x term over here. We have this sine of x term over here. Last time I just factored it out to the front. Can I do the same thing here? Not really, because I have this middle term of cosine of x sine of h, which doesn't have a sine of x in it. All right, so that's kind of making things a little bit annoying. But to kind of try to do what I did with the e to the x, let's maybe shuffle things around. So like the sine of x's are by each other, and then the non-sine of x's are by each other. So we'll call this the limit as h approaches 0. And I'm going to try to do the same thing where I get like the x stuff on the outside and then the non-x stuff left behind on the inside here. It's kind of my goal. So this is going to be sine of x times cosine of h minus sine of x. I'm actually going to go ahead and split this fraction apart into two fractions divided by h plus, big bracket here, cosine of x times sine of h over h. So I've done a couple of steps here. I've rearranged my order, and then I've split it apart into one fraction that has my sine of x's and one fraction that doesn't have my sine of x's, one that has the cosine of x instead. Which is going to feel like a very random thing to do if you don't know how to do this already, which fair enough. Again, not one that I would say is reasonable if, say, we had like a test on Wednesday. Okay. So first of all, what can I do with limits very, very similar to what I saw with B? Rather than taking the limit of a sum, what can I do? Yeah, take each of the individual limits and then add them together at the end. So this should be the same as the limit. You can kind of distribute it. It's not distribution, but you kind of can distribute it, of sine of x times cosine of h minus sine of x over h plus the limit as h approaches 0 of cosine of x times sine of h all over h. Not like terms because of the cosine of h. But because they can't cancel, what can we do with them instead? We could factor them out. Okay. Is the sign of x that we're about to factor out, is that going to be affected at all by the h going to 0? So I'm actually going to factor it like we did with the e to the x. I'm going to move it all the way out to the outside of the limit. This is going to be the same as sine of x times the limit as h approaches 0 of cosine of h minus 1 over h. Yeah, Harrison. You don't have to. It's just this is a limit that we're going to be able to evaluate really easily. Yeah. It's like part of our target is to get to this limit. But how would you know that if you hadn't done this before? I don't know. Plus, and then we're going to do the same thing with the cosine of x, because is the cosine of x going to be affected at all when h goes to 0? No, so I'm just going to move that to the outside as well. Cosine of x times the limit as h goes to 0 of sine of h over h, which is another thing that we're going to care about. That's another thing that we can evaluate directly. And referencing what we did from day 1, very first day of this, example 2, I think the second one is B and the first one is part E, I believe. This is just 0. And this, which actually we've computed a bunch of times using like squeeze theorem and stuff, this is just 1. Which if you weren't sure, you could do the calculator thing, but we've calculated both of those before. Those are 2 things that we've computed before. And so what am I left with for my derivative? All I am left with is cosine of x. Okay, again, way above our pay grade. Like that is not something that I would expect you guys to be able to just be like, oh yeah, I can do that. Let's take the derivative of cosine now already. No. That's like the stuff that you, when you're actually taking calculus, you just memorize that the derivative of sine of x is cosine of x. Like that's, you just memorize that. But there are some that are fairly straightforward, quote unquote, to do by hand, certainly a lot more so than the 2 that we have looked at. And so I want to give you guys some time to work on those, to take a stab at getting those done. One of them is basically any polynomial is going to be pretty straightforward to do by hand. So take a moment to try part A, which is f of x is equal to x cubed. Try to find what f prime of x is going to be. And then I'll give you an extended one. There's one very similar to this on the study guide. Let's try, what haven't I used? We'll do k of x is equal to 1 over x squared. So certainly work on A for x cubed. And then once you have finished that one, these would both be ones that I would consider very reasonable if I don't know we have like a test on. Do a quick run through here. So derivative, we are calculating slope. We need x1, x2, y1, y2. What always are our values going to be for x1 and x2? X and x with a little nudge, x plus h. And if that is the case, what are our values for y1 and y2? X cubed and x plus h cubed. And so our function, f prime of x, is the limit as h approaches 0 of x plus h cubed minus x cubed all over that change in x, which works out to be h. Okay, what do I need to do to simplify this expression? We're going to need to do some Punnett squares, right? We need to take that x plus h cubed term, multiply it out as much as I can, and then we'll see, can we do some simplification there? Hopefully it makes the h cancel. If it doesn't, then we're probably going to be out of luck, but we'll see that it will. So this is x plus h times x plus h times x plus h. I will leave the Punnett squares as a little bit of an exercise to the reader. I get here x squared plus 2hx plus h squared times x plus h. And doing out this multiplication, I get x cubed plus 3hx squared plus 3h squared x plus h cubed. And so my derivative is the limit as h approaches 0 of x cubed plus 3hx squared plus 3h squared x plus h cubed minus x cubed all over h. What do we have here that we can simplify? Yeah, the x cubed here and the x cubed here cancel. So this is the limit as h approaches 0 of 3hx squared plus 3h squared x plus h cubed all over h. And why is this such a big deal to have this? We can factor out an h, which will then cancel with the h in our denominator. Alternatively, you could just remove one h from each of these to get rid of the h that is distributing in the denominator here. I get that this is the limit as approaches 0 of 3x squared plus 3hx plus h squared. Do I have any domain issues anymore? No. So how do I evaluate this limit? Just plug it in. Just plug in 0 for h. I get that this limit is 3x squared. It probably wouldn't make you do it to the fourth, just because that would get kind of annoying. You know, that many Punnett squares is unnecessary for it, but certainly I could. But I probably won't. But like anything cubed, anything squared, that would all be highly reasonable. Very good example on the study guide that walks you, or that has you go through kind of a combination of the two. Questions with example A? Let's look at the setup for the extra example, and then there's a very similar question on the study guide again if you have questions. And if you want to take a look at it tomorrow, I'd be more than happy to. I just want to make sure that you guys do have time to work on your study guides today. What is our derivative setup going to look like for k prime of x? Let's see if we can get a good feel for this. So what is y2 minus y1 over x2 minus x1 going to look like? It's 1 over x squared all over h. And you would match denominators and combine like terms and blah, 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 blah. Cameron. Will it always be x plus h? Is that the question? So like I could give you a function that's like 1 over x plus x. And when we do y2 here, it would be 1 over x plus h like this. But like the h is kind of tied to the x, if that makes sense. Like think of it, it's like it's 4 and then it's 4.00001, right? The 0.000001 never really stands alone. It's always like side by side with the 4. Very good question. And again, I'll leave that one as an exercise. So the reader works out pretty cleanly. And would be a pretty good example if I had, I don't know, say like a test on today. So it would be a pretty good one. Oh, I think that'd be reasonable not for a bonus question. I think that'd be reasonable just for a regular test question. Yeah. All right. So we're going to finish off today by taking a look at an application that does a really, really good job both of highlighting some of the utility behind the derivative, why calculating the derivative, finding the derivative can be so useful. And also kind of really, really hammering in like what this derivative thing is that we have just found. Like we can say, oh, it's a function that tells us the slope of the tangent line, but we're going to see that very much is exactly what it is giving us. And we'll get some practice getting kind of comfortable with that. And the way that we are going to do that is I'm saying that it is the slope of the tangent line that passes through the function. We're actually going to find the equations to the tangent lines that are passing through functions at particular points. So let's consider example 2 here, where we are being asked to find the equation of the line tangent to our given function when x is equal to 0. Now, we're thinking about the equation to a line. What are our two different ways or different formulas that we have for finding the equation of a line? So y equals mx plus b, which is fine, but I don't love the fact that b is so specific. And so what's the more generic one that I like a lot more? Is y minus y1, we replace the y2, is equal to m times x minus x1. So you have point slope form, which I like a lot because it's very generic. And then if you want to, you can do y equals mx plus b. It's fine, but you have to do more work. And I don't know why you would do more work when you could choose to do less work. So what are the two essential pieces of information that we need in order to generate the equation of a line? So we need the slope and we need a point, right? It doesn't necessarily need to be the y-intercept. If it is, cool. If it's not, then we can use the second formula. That is also totally fine. So we need slope, we need point. The point comes from the original equation. So for instance, let's take a look at example C here. Let's look at C. What is the point that goes with an x value of 0? How do I find that? So if the point that I care about is 0, what is the accompanying y value? How do I find it? Yeah, we do sine of 0, which is sine of 0. Y value would be 0. Okay, so that's our x1 and that's our y1. So then the only other thing that we need is the slope of our line. And that is where the derivative comes in. In this case, the slope of our line, m, is the same as h prime of that particular x value, in this case, 0. What did we find the derivative of h to be? Cosine of x. So what is cosine of 0? It is 1. And so our tangent line will have the equation y minus y1, which we said was 0, is equal to m, which we found was 1, times x minus x1, or cleaning this up a little bit, y equals x. Yes, this is the equation of the tangent line. It is not necessarily, it's not the function itself. But another way to think about this is the linear approximation, or a linear approximation, I should say, at x equals 0. Which means that if we were asked to compute values or outputs for our function around 0, this function does a pretty good job of doing that, and it might be difficult to get similar results from sine. For instance, if I wanted to know, or if I wanted to guess at what sine of 0.1 is that a unit circle angle? No, that would be pretty hard to directly compute. But I know that around 0, my function acts like the line y equals x. And so we would predict that this should be about 0.1. It should-ish somewhat follow the trajectory that our linear approximation predicts. Is it going to be exact? No, it's going to be off by a little bit. But at the very least, it does a decent job of guessing what's going on around 0. And just to kind of highlight that, because I think that this is kind of cool, if we look at sine of x, and we are looking at the line y equals 0, you'll notice that when we're really, really close to 0, the two are basically impossible to tell apart. So it is the linear approximation and also the tangent line at y equals 0. Or at when x is equal to 0, rather, I should say. Now, could we have done this for some other point? Absolutely. You could do this for really any point, and construct a tangent line, and you'll notice that the tangent line does a really good job of kind of tracing out the slope at that particular point, which is, its job. It's what you would expect it to do. Questions with finding the equation to a tangent line? Which would also be, I don't know if we had like a test on Wednesday, a really good question to show up on that test, hypothetically. Hey, I even like the extension of using it to make predictions about what's going on. Kind of a cool little application there. Yeah. The final answer would be y equals x. And then the red is just how we could use that equation, like some applications of that equation, right? It's certainly possible. certainly good. Certainly good. Yeah. So for instance, let's take a look at A. Let's take a look at A here. Let's do it with 0. And then I want to show it, case it without 0 as well, because I think it's a good example to look at without. So let's try with 0 first, and then that's going to be a very boring answer. And then let's look at what's happening elsewhere. For x is equal to 0, what is the point? So if our x1 is equal to 0, what is the corresponding y value going to be? Also 0, right? 0 cubed is in fact 0. And then how do I find slope? Well, before, but now we have a formula. What was our formula for slope? Well, that we found for this specific function. Yeah, y equals 3x squared, right? That was our derivative. So just a reminder, f prime, we said was 3x squared. Here we said g prime was e to the x, and here we said h prime was cosine of x. So in this case, our slope is going to be f prime of 0, which is 3 times 0 squared. Not particularly interesting. It is just 0. And so plugging into our y minus y1, blah, 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 and simplifying, we would get the equation y equals 0. Again, not a very interesting one. What's going on at y equals 0. But again, we could see that in the graph. If we were to look at our, in this case, green and our blue, notice that the distance between the two, that the kind of error between those two is very, very small when we are very, very close to 0. Y equals 0 actually does a pretty good job of describing what x cubed is doing right around there. But the reason why the derivative is generic is because we would expect the slope to change at different values of x. We'd expect it to get steeper for some values of x, less steep for others. So here it's y equals 0. But let's examine somewhere else. Let's take a look at what's going on when x is equal to 1 instead of when x is equal to 0. Because at 0, it's kind of boring. So let's look at x is equal to 1. What is the corresponding y value when x is equal to 1? Just 1, okay. And then what is the slope if I'm trying to do f prime of 1? 3 times 1 squared, which is 3. Just 3, right? Square first, then multiply. And so the equation to our line is y minus 1 is equal to 3 times x minus 1. You could simplify this. I don't really need us to. And we could see that at that point for that line, we also are doing a very good job of approximating what our function is doing. And so we have this like evolving kind of tangent function that does a really, really, really good job of making predictions about what is going on with our point. Actually, I can do this in a really clever way with Desmos. Let me set this up. Let's change this to let's change this to a cubed because that's our function. And then we'll change this to 3 times a squared. That's how we're finding the slope. If I add in a slider for a, you'll notice that. What did I do wrong here? X minus, this should be x minus a, sorry. X minus a. There we go. You'll notice that this is really cool. Our line does a really, really, really good job of kind of like sticking to the function like that. That's what our derivative is doing, is it's keeping that line kind of stuck to what's going on.